Before that, I want good afternoon, all of you. In a short while, we will be conducting technical session 4 of eSESTEC 2020. Before that, I would like to make some important announcement. First of all the participants are requested to switch off their videos regarding the presentation. Then, if you have any query, please write in the chat box of eSESTEC 2020 host. And if you have any problems regarding the communication, kindly contact directly to our host SESTEC team. Thank you. Now coming to technical session 4. The technical session 4 will be chaired by Shri DS Director MFG, who joined DRC in 1988 after successful completion of training school from 31st batch of training school of VARC. He had worked 27 years in the field of reactor component designing, structural integrity assessment, and assessment of component fitness for several power reactors in India. Shri Bhasin currently leading the research and the development program for fuel and fuel-related component fabrications, development for present and futuristic reactors under Indian Nuclear Program. He has received several awards, namely Indian Nuclear Society Medal in 2002 for his contribution to nuclear science and technology, DAE SRC Science and Technology Award 2006, several DAE Group Achievement Awards, as well as the prestigious Homi Bhabha Science and Technology Award. He is a fellow of Indian National Academy of Engineering. He has authored 300 publications in different research fields of nuclear science and engineering. On the behalf of organizing committee, I request Sir to kindly share the session. Thank you.
Thanks to the organizing team of eSESTEC, and welcome everybody in this fourth session of emerging trends in separation science and technology. In this session, we have very two interesting plenary talks, one from Spain and the other from India. So the first talk is from Spain by Dr. Immobilized Ortiz. Currently, she is professor at chemical engineering, professor of chemical engineering at the University of Cantabria, Spain, and the position she has held since 1996. And also, she is heading their advanced separation process research group. She completed her PhD in the year 1985 from Spain, and visiting professor at Wuhan University, China in 2010, and Fulbright fellow at Carnegie Mellon University, USA. Her research areas include design optimization and integration of advanced separation technologies, which includes the synthesis and development of high selective separation media, integration of separation technologies, searching for more efficient separations, and developing the methodology for process scale-up and scale-up. She has supervised 42 doctorate theses. She was elected to National Academy of Sciences in the year 2008 and has received several research awards, some of them like 15 Rodinola Research Prize for the work of industrial application for membrane technologies, and there are several others. So, Dr. Ortiz will be talking on the paper titled Membrane Assisted Photocatalytic Reactors Achieving the Paradigm of Process Integration. So we'll invite Dr. Ortiz for this presentation. Yes, you may start.
Good afternoon. First of all, I'd like to thank the organizers of this conference for having extended the invitation to give this plenary talk on membrane reactors.
Sorry.
By the International Union for Theory of Biochemistry. According to
Can you see the screen? Can you see the full screen?
It is not shared, ma'am.
It is not here.
To remove products of the reactor.
So let's start again.
These membrane reactors are multifunctional.
So
Good afternoon.
now,
First of all, I'd like to
No, ma'am. It's still not.
but you don't hear or you don't see the screen.
We can. You can hear the recording,
Yes, you can hear the recording.
but no sharing is there.
No sharing. So let's start again. So can you give me permission to share the screen?
I'm already given you the presenter. You must have a share button. Yes, now it is sharing.
Now it is sharing, but
Yes.
I think that I need to share the other screen. So let's start and see what happens. What do you see now?
It's the screen you are seeing in your laptop. There's two breaks in.
So I need to share the other screen.
Yes, ma'am.
Good afternoon.
Yes, the duplicate presenter.
Now.
No.
No?
No.
You cannot see the screen now and here?
I can see the screen, but it is the back ends of the screen. That is the front page and next page. Both are coming.
Membrane reactors. Considering the fundamentals, application,
The lower option.
and to eventually
Yes, ma'am.
future perspectives. Let's start with the definition provided by the International Union for Pure and Applied Chemistry. According to this definition, a membrane reactor comprises of a reaction chamber along with a membrane to add reactants or to remove products of the reaction. Thus, these membrane reactors are multifunctional units that accomplish the process integration parallel. Membrane reactors have mostly focused on the integration of catalysis and membranes. What is the role of a membrane in a membrane reactor? So, for a given reaction between two reactants, A and B, so give two products, C and D, the membrane can play different roles. First, the membrane can facilitate the removal of one or more products from the reactor, thus increasing the reaction, promoting the reaction, and shifting the thermodynamic equilibrium. But there is a second possibility where the membrane facilitates the distribution of one or more reactants, and in this way, it promotes a more uniform reaction and avoids the formation of cold and hot spots. And there is also a third possibility where the catalytic membrane is installed in order to improve contact of the reactants, increasing the catalytic activity. The first applications of membrane reactors date back to the 1970s with the use of polymeric membranes for enzymatic reactions and metallic membranes for high temperature reactions. When an enzymatic reactor is coupled to a membrane unit, microfiltration or ultrafiltration membrane unit, this membrane retains the catalyst that can be recycled back to the reaction zone, increasing the effectiveness of the reaction, and the products of the reaction permeate through the pores of the membrane. At industrial scale, it's worth mentioning the development of a platform technology at the USA for catalyst separation and recovery. When a photocatalytic reaction is combined with a membrane unit, the result is called photocatalytic membrane reactor. Photocatalytic reactions belong to the group of advanced oxidation processes that are based on the use of light irradiation together with the semiconductor. During the photocatalytic degradation, highly oxidizing radical species are formed that break the molecules into smaller molecules. Most applications have focused on the treatment of wastewater and water remediation. Integration of photocatalytic processes and membrane units can be done straightforwardly due to the similar operative conditions of both processes, such as low temperature and pressures and low concentration of the target solutes. The membrane here can act as a filtration medium, having the photocatalyst suspended in the solution, or can facilitate the support of the catalyst, constituting a photocatalytic membrane. For the performance of a photocatalytic membrane reactor, the key elements are first the photocatalyst and its characteristics, the membrane type and characteristics, and third, the photocatalytic membrane reactor configuration. So next, let's go through the main characteristics and properties of these three elements. Starting with photocatalyst, in heterogeneous photocatalysis, when a semiconductor is irradiated by light with energy that matches or is greater than the energy band gap of the semiconductor, an electron from a field valence band is excited to a vacant conduction band, leaving behind a hole in the valence band. These valence band holes are powerful oxidants, whereas the conduction band electrons are powerful reactants. They can be transferred to the surface of the photocatalyst and react with oxygen-containing molecules, such as dissolved oxygen, to give superoxide radicals, or with water to give hydroxyl radicals. However, they can recombine between themselves, either in bulk or on the surface of the photocatalyst, losing photocatalytic activity. The first use of titanium oxide date back was reported by Fukushima and Honda in 1972 for water splitting. The positive characteristics, besides the high photoreactivity and cost effectiveness, the commercial availability, and the chemical resistance in a wide pH range, resistance to photocorrosion, as well as thermal stability, promoted the applications of this semiconductor. But on the negative side, the energy is mainly absorbed in the UV region due to its relatively large band gap. And the recombination of charge carriers, either in bulk or on the surface of the catalyst, take place at a much higher rate than the interfacial transfer of charge carriers. Accordingly, the photocatalytic activity of titanium oxide can be improved by employing strategies that prevent bulk or surface charge recombination and enhance the rate of charge transfer to the surface of titanium oxide. Within this objective, doping titanium oxide with noble metals such as platinum, gold, silver, or rhodium has been a strategy widely researched in order to improve the performance of the photocatalyst, to reduce the charge carriers recombination rate, as well as to reduce the band gap energy of the photocatalyst, thus shifting the radiation absorption towards higher wavelengths and permitting the use of visible light. Noble metals can serve as a sink for the photogenerated electrons while forming a Schottky barrier with titanium oxide. And in this way, the composite photocatalyst reduced the rate of charge carrier recombination. Moreover, the localized surface plasmon resonance effect, which is the collective electron oscillation on the surface of noble metals, contributes to the absorption of visible light. Next, to better understand the role and characteristics of the membranes, let's summarize the main configurations of photocatalytic membrane reactor. In the first configuration, the photocatalyst is suspended in the solution, and this configuration is referred to as suspended photocatalytic membrane reactor or slurry type photocatalytic membrane reactor. The suspended photocatalytic provide a large contact area with the solutes of the solution, increasing the photocatalytic activity. But the particles can be deposited on the membrane surface, leading to fouling properties and resulting in flux decline through the membrane. Additionally, this configuration needs of a further step for the photocatalyst particles separation and recovery, increasing the operation cost. The membrane can be immersed in the solution, and in this way it is exposed to radiation light and also to the oxidation effect of radical oxidation species generated during the photocatalytic degradation reactions. And in a second alternative, it can be placed outside the reaction container. If the membrane is protected, the solution must be pumped through the membrane unit, and this needs high pressure for pumping the solution and increases the risk of membrane fouling by the photocatalyst particles. The submerged membrane configuration has known an increased number of applications and studies since the work by Pu et al. On the purification of drinking water. Air flows through the solution and keeps the particles of the photocatalyst suspended and prevents the deposition of those particles on the membrane surface. In order to protect the membrane from light irradiation, baffles can be put inside the reactor, acting as light shields. The presence of the particles in the solution and turbidity of the solution leads to a scattering of ultraviolet light, and with this reduces the photoactivity of the process. Fouling of the membrane damages the membrane and reduces the radiation flux through it. And it's also a risk that the membrane can be deformed through light exposure. Literature contains a wide number of reports on innovative solutions to enhance the performance of submerged membrane reactors. Recently, Molinari et al. Reported a device with a submerged membrane that was coupled to an oscillatory movement with the aim to keep the particles suspended in the solution and prevent deposition on the membrane surface. This device was successfully applied to cosmetics and some pharmaceuticals using zinc oxide as semiconductor. And the authors reported a high degradation yield of all the solutes. The second configuration of photocatalytic membranes is referred to as immobilized photocatalytic membrane reactor. Here, the catalyst is supported on the membrane, and as so, it acts as a barrier for the solutes that are kept in the solution, and it acts also as support for the photocatalyst. The Contact between the solutes and the catalyst is hindered by the mass transport that must be overcome. And the configuration facilitates considerably the further separation and reuse of the catalyst that is very convenient for continuous operation mode with regard to the catalyst. In this picture, the photocatalytic membrane is immersed in the solution. This is applied to the analysis of newly synthesized membranes in small-scale operation mode. But for large-scale operation, continuous flow of the solution is more convenient, either in depth infiltration mode or the most convenient for industrial applications and large-scale applications, cross-flow configuration. The question now is, how are the photocatalytic membranes fabricated? So the most extended method is coating the surface of the membrane with the photocatalyst. Let's consider first polymeric materials, microporous polymeric materials. So both surfaces of the polymeric materials can be coated with the photocatalyst, and following different techniques such as the coating, electrospraying, magnetosculpturing, and deposition of gas phase photocatalysts. After coating, the membrane permeability decreases because the pores are black. And with the permeability decrease, there is a decrease in the flux, in the permeation flux. However, there are positive properties inherent to this coating procedure, such as an increase in the hydrophilicity of the resultant membrane that provides anti-fouling resistance. And this coating protects against UV damage and against radical oxidation species damage. But with long operation times, part of the coating is leached out from the membrane, and this needs additional functionalization steps to prevent the catalyst loss. Although polymeric materials have been widely used in the fabrication of photocatalytic membranes, the higher resistance, mechanical, thermal, and chemical resistance of inorganic supports have led to a large number of studies and research works. The fabrication methods have been adapted and in a way are similar to the fabrication methods followed for polymeric photocatalytic membranes. In this picture, silane oxide nanoparticles are sprayed on a stainless steel mesh, and the photocatalytic membrane has been successfully applied to the degradation of methylene blue. A good review on application of ceramic-based photocatalytic membrane based on the support of titanium oxide on ceramic materials has been recently published, collecting the works published over 15 years, but the processing cost of ceramic materials are still higher than the processing cost of polymeric materials. Thus, for industrial applications and industrial penetration, the ceramic technology needs to be further improved. Recently, Fraga et al. Reported the fabrication of a new membrane by supporting P25 titanium oxide nanoparticles on a commercial high-flux sheet silicon carbide membrane. The photocatalyst was supported on both faces of the membrane, and the photocatalytic membrane was immersed in olive mill wastewaters. The yield in the degradation of the main parameters, such as chemical oxygen demand, total organic carbon, phenolic compounds, and so on, was very high. And according to the authors, the cuboid shape of the membrane facilitates considerably the process scale up. Let's consider now the applications of photocatalytic membrane reactors. Wastewater treatment and water remediation is the sector that has received an increased attention in the last 4 to 5 decades. the degradation of a large number of micropollutants, recalcitrant pollutants, non-biodegradable pollutants, and also research of a large number of wastewater sources has been carried out working with photocatalytic membrane reactors. But there is also a second sector aimed at the synthesis of chemicals, either by partial oxidation or by partial hydrogenation, that has employed photocatalytic membrane reactors. Here, the possibility to control the residence strength of reactants or products according to the different roles that the membrane can play is an advantage. In this group, it deserves special attention the photocatalytic generation of hydrogen. In the field of wastewater treatment and water remediation, a considerable progress has been made. The synthesis of new photocatalytic membrane by supporting novel metals doped titanium oxide, such as silver doped titanium oxide on ceramic materials, multifunctional membranes have been constructed with different functions and simultaneous functions, such as chemical free disinfection, together with the oxidation of organic compounds and reducing membrane fouling, and also providing a self-cleaning function of the catalyst that enables maintaining a constant permeation flux. Therefore, from an economic point of view, the cleaning frequency is reduced, and with this, the cost of cleaning agents is also reduced. In the field of chemical synthesis, the capacity to control the residence strength avoids the formation of secondary reactions and improves the selectivity of the products. Photocatalytic membrane reactors have been employed for the oxidation of cyclohexane, of benzene, of aromatic alcohols, or oxidation of ferulic acid to vanillin. And in the group of reactions, hydrogenation of acetophenone, photocatalytic generation of hydrogen, and more recently, CO2 reduction and nitrite reduction to ammonia are motivating examples. Some words on the photocatalytic generation of hydrogen. Since the work reported in 1972 by Fukushima and Honda on water splitting, there has been a large number of studies and research works published in literature. The simplest configuration of a photocatalytic cell for hydrogen generation consists of two chambers separated by a membrane that allows the transfer of electrons thanks to a redox couple such as iron 3, iron 2. In one of the chambers, oxidation of water takes place through oxygen, and in the second chamber, the generation of hydrogen takes place. For this, two different photocatalysts are needed, one for the oxidation of water and the second one for the generation of hydrogen. A large number of photocatalysts have been synthesized and tried for this purpose. Doping titanium oxide with novel metals deserves a special mention. This system mimics the set-scheme mechanisms of photocatalytic semiconductors. Reducing membrane fouling is a constant in many works reported in literature and in many applications of photocatalytic membrane reactors. One alternative consists in the development and configuration of hybrid processes, where the photocatalytic membrane reactor is coupled to a membrane unit working at low pressure. Substituting high pressure filtration by low pressure filtration or low pressure permeation, membrane permeation, decreases membrane fouling. Examples of hybridization of photocatalytic processes with membrane distillation, with perforation, and with dialysis have been applied in the field of wastewater treatment and in the synthesis of chemicals. Coupled photocatalysis with membrane distillation. Here, after the photodegradation of the solutes contained in the solution is pumped to the membrane distillation unit. Here, a hydrophobic polymeric material is used, and the solvent, together with the small-sized solutes, permeate through the pores of the membrane in vapor phase and are collected in the permeate site. This has been applied to the degradation of pharmaceuticals from tap water. The fouling of the membrane due to the deposition of the photocatalyst particles is considerably reduced as the pressure of the fixed solution is near atmospheric pressure. But the system is energy intensive as there is the need to evaporate the solution, and the permeation flux is lower when compared to high pressure filtration units. The second hybrid process consists of combining photocatalytic degradation with evaporation. This has been applied to the removal of 4-chlorophenol from polluted waters and also to the partial oxidation of transferolic acid with the aim of obtaining vanillin and aroma. Here, the process is similar, but the membrane is different to the membrane used in membrane distillation units. The membrane is a dense polymeric material where the solutes are solubilized and then diffused to the permeate site. The driving force is the pressure difference between the fixed solution and the permeate site, and is created by vacuum in the permeate site. So this process adds a considerable selectivity thanks to the solubility of the solute on the membrane, and is especially indicated for the selective separation and recovery of volatile components such as aroma components. The coupling of photocatalytic degradation with dialysis membranes has been applied to the mineralization of organic compounds contained in turbid waters. Dialysis is a process driven by the chemical potential difference between both sides of the membrane without applying a transmembrane pressure. Contaminants diffuse from the higher chemical potential side to the lower chemical potential side. And the membrane helps to keep the particles in their original compartments. The membrane provides a high selectivity towards the solute, but the permeation flux through the membrane is low when compared to high pressure filtration units. So, coming to the end of this lecture, let's collect the challenges and the perspective to solve these challenges. Starting with the photocatalyst, nowadays, low usage of visible light is one of the challenges to be overcome, as it is fast charge recombination by most of the photocatalysts and low migration ability of the photogenerated electrons and holes. Thus, the guidelines is to develop composite catalysts by incorporation of co-catalysts which alter the photocatalytic mechanism and are active under solar light, and gap tuning, and they operate with high stability. Non-metal and metalloid elements are cost-effective and eco-friendly as compared with novel metals and transition metals. And the idea is to eventually exploit the sun as a cheap and clean source of energy. With regard to the membranes, there is the need to reduce membrane fouling. Membrane fouling is higher when pressure-driven filtration is applied. So alternatives such as submerged membrane or hybrid systems with low pressure-driven membrane units should be promoted. There is also another problem related to the oxidation and damage of polymeric materials by UV light and by radical oxidation species. So the alternatives consist of using polymeric materials with higher antifouling resistance and resistance to UV and ROS species. So finally, the development of fouling-resistant and more photocatalytically active membranes that can be solar light driven, which incorporate desired properties such as high crystallinity, high surface area, and high nanoscale toughness, is the guideline in this part. With regard to reactor design, both configurations, suspended photocatalytic membrane reactors and immobilized photocatalytic membrane reactors, need further research and improvement. In the first case, at present they have greater perspective of industrial applications, because they can use commercial membranes suitable also for non-photocatalytic applications. And they have the possibility to separate the reaction zone and the separation zone. But further research must be done on the recoverability of the suspended photocatalysts. Immobilized photocatalytic membrane reactors offer the possibility to operate in continuous mode with respect to the photocatalyst. This is very convenient for large-scale applications. So tailored photocatalytic membranes and membrane modules with acceptable cost, stable in a wide range of operative conditions, resistant to fouling, and showing high and reproducible performance over long terms need to be developed. And in addition, for this type of configuration, advanced modeling and control of mass transfer limitations in advanced configurations of photocatalytic membrane reactors is needed to facilitate process design and scale-up. And finally, some comments on process and plant design. Increased applications with real wastewaters and pollute waters containing the common pollutants such as salts, dissolved organic matter together with the targeted pollutants should be carried out. In many of the reported works, dyes have been used, and dyes act as photosensitizers themselves. They can inject an electron into the catalyst conduction band, causing activation, and this makes difficult to attribute the degradation to a purely photocatalytic effect. Besides, long-term reliability of the photocatalytic system by harvesting natural light for real water and wastewater treatment is needed. Incidents of weather changes should be assessed, especially sunlight. Also, changes in pollutant concentration and in the properties of wastewater. And finally, more advanced flow sheets combining photocatalytic membrane reactors with cost-effective biological systems, especially in the field of wastewater treatment, should be considered. I would like to finish this lecture without expressing my acknowledgement to my coworkers and students, starting with Dr. Maria José Rivero. She has been my coworker for many years, working on different applications of photocatalysis. In the field of wastewater treatment, starting with the remediation of gray waters to the more recent generation of hydrogen. She has been involved in the synthesis and characterization of new composite photocatalysts and on the optimum design of photocatalytic processes. Postdocs will join our group, Dr. Olaya Iglesias, who was the first researcher in our group working with the photocatalytic generation of hydrogen, and more recently, Dr. Marta Rumayor, who is involved in the environmental assessment of photocatalytic processes using life cycle assessment tools. PhD students who work in our group and after having finished the PhD, some of them joined academia and others were hired by industry and by different companies. Dr. Oscar Primo, he was the first researcher working on the application of advanced oxidation processes to the remediation of landfill leachates. In this case, he contemplated also the use of photo-assisted oxidation processes. Dr. Sara Dominguez, who did great work on the photocatalytic removal of emerging contaminants. Dr. Javier Escudero, who made the comparison between photocatalytic and electrocatalytic treatment of waters containing organic compounds. Nowadays, he has joined the university at Guanajuato, Mexico. Dr. Paula Ribao, who did an outstanding work on the synthesis, characterization, and application of composites that where titanium oxide was doped with noble metals or with graphene oxide. Dr. Jennifer Gomez, who studied the magnetic separation of magnetically recoverable photocatalysts. Juan Corredor, who is about to defend his thesis on the photocatalytic generation of hydrogen. The students who have recently joined our group, such as Laura Rancaño, working on the modeling of new photocatalytic applications, Carmen Martin, working on the magnetically recoverable photocatalyst, and Deva Pelayo, working on the integrated disinfection and degradation of secondary wastewater. And finally, I'd like to thank all of you for your attention, and I will be happy to answer any questions you may have. Goodbye.
Thank you, Dr. Cortez, for enlightening presentation on membrane-assisted photocatalytic reactors. The session is now open for questions. 2 questions have already been raised. I just conveyed this to you on behalf of whether PMRs can be used for selective oxidation or selective reduction of metals too.
So can you repeat the question, please?
Whether PMRs can be
Yes.
used for selective oxidation or selective reduction of metals too.
Or selective?
Reduction.
Yes.
Selective oxidation or selective reduction.
Both. So
I mean,
this is a new field. This is a new field of research. This the application of PMR to wastewater treatment has known more studies, but selective reduction and oxidation is a new field of research. The advantages is that having the membrane allows to control the residence time either of reactants or of the products of reaction. By controlling the residence time, the reactions pathway can be controlled. Applications to oxidation are more favorable than applications to reduction because the holes are powerful oxidants, but the conduction band electrons are reductants, but the power is not as high as the power of reductant agents. The point is the key point here is the catalyst that is being used, and one of the selective reduction reactions is the generation of hydrogen. The reduction of hydrogen has generated an increased deal of attention for many decades, and the idea is to use photoreforming of wastes to, at the same time that wastes are degraded, to generate hydrogen. This is one of the examples of selective reduction. And in the field of selective oxidation, yes, there are several examples that are considered in literature where PMRs have been used.
Okay, thank you. Another question is, what about the regeneration ability of these polymeric membranes and for how long the efficiency remains high?
So the intervention,
I'll repeat again. What about the regeneration ability of these polymeric membranes? And for how long the efficiency remains high?
I'm not sure that I have listened completely to your question because your voice is cut. So I try to repeat the question. So your question refers to the lifetime of polymeric membranes?
Regeneration ability of polymeric membranes.
Okay. The regeneration, okay. So PMRs are classified in two different groups. The first group uses the membranes, either polymeric or ceramic, as filtration medium. So here the problem is fouling by the catalyst particles, by the photocatalyst particles, and to prevent fouling with commercial membranes, a maintenance protocol should be done, similar to filtration operations when using microfiltration or ultrafiltration units, and when the water contains solids. The protocols are similar in this case, where membranes have the role of filtration. Whereas the second type, where the membranes, apart from filtration, they act as support for the catalyst, here is different because fouling is softer. So there is not the problem of fouling is not as hard as it is when membranes are used as filtration, because there are not solid particles. And the idea with these immobilized catalysts is that they can be used for longer times in working in a continuous mode with regard to the catalyst and with regard to the solids.
Okay, so we'll thank Dr. Ortiz for very lively presentation and advancements in the area of membrane-assisted photocatalytic reactors.
Okay, you're welcome.
We move on to the next plenary talk, that is by Dr. Jaydeep Chatterjee. Dr. Jaydeep is Professor of Chemical Engineering at BITS Pilani University, which is, of course, at Hyderabad campus. He did his PhD in Chemical Engineering from Illinois Institute of Technology, Chicago, and his area of expertise is primarily to develop proprietary technologies for water purification. Earlier, he had been General Manager at LD Ultra Industries, Coimbatore, where he was leading program to develop new water purification products. Prior to that, he was principal scientist and group leader at Unilever Research, Bangalore, as a lead strategic science group in water and separation science. And still prior to that, he held many other positions as scientist in various like Unilever Research, etc. He is a member of American Chemical Society and Indian Society for Surface and Science and Technology. He has published several journal publications and he has about 35 patents. Dr. Jaydeep will be giving a talk on a novel technology for separation of dissolved surfactants from aqueous solutions. We'll invite Dr. Jaydeep Chatterjee. You may start now.
Okay, thank you very much for the invitation. So I just need a confirmation that you can see my presentation.
Yes, it is visible.
Okay, thank you very much. So my sincere thanks to the organizers of the conference for inviting me for this talk. I'll talk about a new separation technology which can be used to remove dissolved surfactants from water, so that this water could be wastewater. And the context is that, you can, okay, I'll just go through the first couple of slides, which will put it in context. Okay. So I'm currently, it was introduced, I'm a professor of chemical engineering at BITS Pilani, Hyderabad campus. Now, introduction. Surfactant containing products are used every day. We are using multiple products and which have surfactants. Typically, these are detergent products for cleaning clothes, for cleaning ourselves, for soaps, of course. These are also surfactants, and then for a host of other cleaning applications. This leads to a steady amount of surfactants being present in municipal wastewater. The reason I've written temporary there, because there's a half-life is not beyond a couple of days. And so it will get naturally biodegraded in wastewater, provided the concentrations are not too high. I mean, it can lead to a multiple set of problems, large concentrations, which is what I'll talk about. The generation of surfactant-rich wastewater also occurs in factories which are dealing with these products, because we often, due to general sanitization practices and the mixing vessels have to be cleaned out and sanitized. This leads to very high surfactant-containing wastewaters, which can cause a problem in conventional wastewater treatment plants. Yeah, so this is really a new exploration that we did, and some of the results we'll talk about. Yeah. Now, we know I used to live in Bangalore some time back. And at that time, occasionally on my way to work in the morning, we'd see scenes like this and this. Okay, so those of you who are from Bangalore, you might have experienced this. There are certain lakes in Bangalore which just foam over. Yeah, so it's a traffic nuisance. It's, of course, maybe a health hazard as well. Multiple issues, and naturally, yeah. So this is, I'm not saying this is a direct consequence of the use of those surfactants, but certainly if you get foam in water, it means some surface active molecule must be there. For reasons I will, for those who are not initiated into the subject will, maybe appreciate it. So novel technology so this is also a motivation, so how can we deal with this excessive foaming and foaming wastewaters? Because once a foam is generated, it forms a coat over the water, preventing exchange, oxygen dissolution and things like that over. Yeah. So now, very basically, what is the structure of foam? Foam can be viewed as structured water, because it's, after all, most of the mass of the foam is in the water. There's, of course, air trapped in it. So, if you make a bubble, a little bubble of air underwater, and if the water has surface active agents, which means surfactant molecules, which are molecules which are having a hydrophilic end, given by the red circles here, shown by the red circles, and a hydrophobic end, which if preferably linear. The hydrophobic end tends to be in air away from water, where the hydrophilic end tends to remain in the water. So since some of the commercial use surfactants are molecules which have the high ability to quickly occupy the interface generated. If they didn't have the ability to quickly occupy the interface generated, they would not be very effective in foaming agents. Yeah. So these molecules will go and form a film or a layer of adsorbed molecules at the interface. All students of interface science and surfactant science would know this. And that results in a layer of a thin film of water which is stabilized. Stabilized due to multiple factors. One is that there may be some electrostatic repulsion between the head groups, or even between the double layers surrounding the head groups, which would be of like charge. There, some of the interactions are steric also, so some of the common misconceptions around foam that I found, one is that the surface tension is low surface tension causes. Well, there are plenty of liquids with very low surface tensions which don't support foam for a long time. So it is the steric stabilization in summary, which is the key criteria required to keep that film there. Otherwise, so once you start blowing air bubbles into the water, the surface of the air bubble will get stabilized with the surfactant molecules. Air being lighter will go to the top, and as more air comes in, the air gets pushed up, and you generate a whole layer of air bubbles which are separated by a stable aqueous film. Yeah. I've taken some of the schematics from this. So steric stabilization of interface prevents foam destabilization, one of the main. So you know very well, many of you may have studied, in this domain. So as the air bubbles go higher, they tend to grow, the films get thinner, this transfer from spherical shapes to all kinds of hexagonal, complex geometrical figures. But that's not the main point here. What happens, what we would observe if we age the foam, there are given by, so the liquid in the films starts to drain out under the influence of gravity. So liquid water, typically, let's talk about aqueous foams. So the water starts draining out, and what you are left with eventually is like a skeletal structure containing the surfactant molecules. Of course, eventually the foam collapses, but as you age it, the films thin, and thinning of the films leads to some changes which I'll talk about now. So general observations will be, if you were to keep making, if you had a very surfactant rich solution here at the bottom, let me start the laser pointer. And so if you are at the bottom and you're blowing bubbles into the water, the bubbles will collect at the top, liquid starts draining out. You keep on blowing bubbles, now the sort of drained out foam is lifted further up, the liquid drains out further, making a very dry foam at the top. Now, the main aspects here are liquid water drains under gravity, leaving the foam drier as it drains out. Higher residence foam leads to drier foam. Yeah. And the surfactant, now these are the critical things that enable this technology that I'm going to talk about. The surfactant mass in the foam, and this is what we found experimentally, remains almost invariant with the residence time. By residence time, I mean the age of the foam. Since the experiments and eventually the process is carried out in a closed chamber with a directed exit for air, we are using the term residence time, but residence time is really the age of the foam once it has left the water phase, the continuous medium, the solution. And the surfactant mass, actually, what we found doesn't drop much or remains largely same. So higher residence time means that water drains out, but the surfactant doesn't, leaving a surfactant-rich structure. So essentially, that's what we are aiming at. So can we get surfactants out of the surfactant-rich structure, which is what I'll just show you. So so airflow rate obviously is, because once the dimensions of the column are fixed, you will fill the volume, and the rate at which you're displacing the air is what the air you're putting in. See, one simplifying assumption, will come to the model and state the simplifying assumptions. So, and if an apparatus is made where you take a surfactant solution, say this is a total capacity of 50 liters, and you take some surfactant solution and blow air bubbles into it, the foam is generated, and the foam will displace the air which is exiting through a hole in the system upstream. Otherwise, it's largely closed. Now, as you keep blowing more air into it, air bubbles into it, you will push the foam out through some conveyor pipes into a mechanical contraption, which is capable of instantaneously collapsing the foam at a high volumetric flow rate, thereby separating the foam into an air which exits from the top and a liquid concentrate which you can collect. So all the surfactant in this solution here, if we can do this right, which I'll talk about, will be taken out as a dry foam. The dry foam will be collapsed. Air will exit the system from which was trapped in the foam, and the liquid concentrate will be available for whatever application that you might want. Yeah. So the two critical variables here to take this forward, we define these two parameters. One is the surfactant content of the foam in milligrams of surfactant per liter of foam produced. And second is the water content of the foam, which is again milliliters of water per liter of foam produced. And the liters of foam produced is almost same to the liters of air blown in. When we plot the variation of these two parameters with the residence time of the foam within the chamber, which simple way to estimate is take the volume and divide it by the volumetric flow rate, what we observed is that the surfactant content of the foam, the SF number, does not change with increase in residence time. Whereas the water content, for the reasons I've just pointed out, shows almost a log linear decline. Yeah. So while these are some computed number, the data is almost matching, would be matching. Yeah. So here we have a rapid decline in the water fraction. Therefore, the concentrate becomes richer the more residence time I give it. Yeah. Now, once again, so this was then scaled up from a lab scale to a plant scale. You could go for 5 kiloliter, 10 kiloliter drum, you can imagine, with some amount of surfactant-rich wastewater. And you would take it at the bottom and aerate it in a similar fashion. The main parts of this section are that you need a closed chamber. The foam is going to get directed into the foam breaking contraption. It's a mechanical device which is electrically powered, consuming few watts of electrical energy. In the lab scale, in the process scale, maybe 100 watts. Yeah, so it's like a small electrical appliance. Yeah. So 2 is surfactant-rich wastewater. 3 are the aerators. The 4th is the air supply. Wastewater inlet, of course, you have to fill the tank. This is a batch treatment process that I'm talking about. So once the water is treated, you can take it out. It is almost, so all the surfactant is removed out from this solution, taken into a concentrate here, and you're left with a largely surfactant-free water if this process can be executed well. Okay, so pipes, so these are the conveyors which will convey the foam. Of course, the foam, if it gets too dry, then it has some trouble flowing. But otherwise, you can literally push it out like a piston using air. So you have this is our mechanical foam breaking. And of course, it's important to remember there's an air vent because all the air in the headspace here has to be vented out eventually. And the foam, and the air in the foam. Yeah, so I think that's, so basic process design is very simple. If I define residence time at the headspace volume divided by the volumetric flow rate of air, that will give me a time in minutes preferably here. And I'll talk, the minutes is a relevant scale. VH is the volume of the headspace, volumetric flow rate of the air. The other next assumption I make is the volume of the foam generated is volumetric flow rate of air into the time for which the operation is carried out, which is the time of the batch process. Now the volume of concentrate removed is the volumetric, the mass of, or the volume, or this is the total volume, so not the rate, sorry. So the volume is time into the volumetric flow rate, and if I take the volume of foam produced into the water fraction of the foam, which is a function of the residence time, I would know exactly how much water I would remove. And this process was scaled up and tested out. And the mass of surfactant removed would be the value of SF per liter. So that's mass of surfactant per liter of foam into the volume of foam in liters. And therefore, you'd get the mass of surfactant and you'd get a desired concentrate. Now, here is the key thing about this process. So one thing we must first understand that the surfactant content in the wastewater, these are the troublesome wastewaters, could be about 1% weight per weight. That means 10 grams per liter or 10,000 ppm. So that's a very large number, and the COD of this number would be more than 20,000. So this is a real headache in the plant because even the wastewater activated sludge conventional biological wastewater treatment plant is not designed to take such high loading of COD. And so this is the 1%, but this is still wastewater. It will be an extremely foamy surfactant rich water, but it's still wastewater. However, if I can convert this into a 10% weight per weight surfactant, then it is a cleaning product. Because if you see our cleaning products, most of the cleaning products available, the surfactant content liquid will vary between 10 to 20%. You know, in high-end detergent, not dishwash, the detergent cleaning liquids, you know, high-end fabric wash liquids, the weight percent will be around 20% typically across a range of products. You can have cleaning products with less than 10% also. So the idea, driving force behind this development was that we can take something which is wastewater and get something that might have some value as in some other application, and leave the water largely free of surfactants, which is otherwise a headache for the downstream process. Because sometimes if the wastewater treatment speed, you know, the biological treatment processes used are slow. So it could be the rate controlling process in the overall plant, because that is one of the slowest transformations occurring. And unless you can throw it out downstream after treatment, everything upstream can get stopped or clogged. So largely, it's a very simple. It's a material balance base. So volume of volume of inlet water, I is the inlet water, concentration of surfactant in it, at any point in time would be equal to the total volume of the top product. Top product is the concentrate. So I've borrowed some terms used typically in chemical engineering, into the concentration of surfactant in the top product, plus the volume of the bottom product, plus the concentration of surfactant in the bottom product. Bottom product is the water that remains in the system. So in the initial volume, so these are the terms I've just defined. So essentially, what are we trying to do? We take input water with say 5,000 ppm or 10,000 ppm, which is 0.5% weight per weight to about 10%, 1% weight per weight. Yeah. So 10,000 ppm, we are trying to split it into a top product, which will be about 10% weight per weight surfactant, which is 1 lakh ppm. Okay. And a bottom product, which is has such a low level of surfactant, 50 milligrams per, around 50 milligrams. The reason is that's about the concentration at which foaming stops. So we can take this process all the way till the water is unable to foam anymore. Its surfactant concentration has dropped so much. Okay, so process description is somewhat like this. So you take your foam large column and you start bubbling air into it through aeration. Of course, the finer the bubble, the better it is, but it shouldn't be require too high a pressure. So typically, this compressed air available in any plant is sufficient for this. The foam displaces the air out from the mechanical contraption, which is can instantaneously collapse the foam. So the foam rises and then it is collapsed, and in the process I just mentioned. The residence time is easy to measure. It's the time taken to displace for the once you start aerating, the time taken for foam to enter the breaker is a rough estimate of the residence time. Because from now on, once you start the process and air is exiting the system and a concentrate is collecting down here, you are basically, it's in a steady mode of operation where surfactant molecules are continuously being picked up from the aqueous phase and deposited into a concentrate on the side. Okay. Now, what is the real challenge here? The real challenge is sort of explained here. Now, imagine you are carrying surfactant molecules out from the drum or the surfactant-rich aqueous solution into a concentrate. If you take too much water along with it, not only will your concentrate be very wet, or concentrate will be dilute, you will also carry out too much water with it. So first you look at the the data on the or the curves shown on the right. So there's a comparison of what would happen if you allowed a 30 minutes residence time for the foam versus a 20-minute residence time for the foam. If you gave a 20 minutes residence time, the foam is still very water rich. So as you run it for several hours, in 18 hours, you would have taken out half the volume. So here, let us assume we are starting with a 1 kiloliter, so 1,000 liters of water. We have carried 500 liters of water out with the foam. Of course, we have taken all the surfactant out as well, but it doesn't help me much because I've only double the concentration of the surfactant in another aqueous pool, which might not be of great value. However, if I allow enough residence time in the or age the foam well enough and it is too dry, then the amount of water it is carrying out is very little, but the surfactant it is carrying out is almost remains the same. So here over 27 hours, I would have removed only about 50 liters from the 1000 liter I started with. And therefore, I still have 950 liters of treated water in the tank, which has been aerated, and all the surfactant has been stripped out. The curves on the left show you the decline of the surfactant concentration in the aqueous phase. The blue line here shows the decline over time. So it's almost a linear decline because the rate at which you are carrying it out, which is basically the air input flow rate, is almost the same. And it will drop from 5000 ppm, say, to below 50 ppm or to a concentration where the foaming stops. Whereas if you do, you would get the similar decline more rapidly if you increase the airflow rate. But that will not do the job twofold because it will carry out too much water, and therefore your concentration of the concentrate will drop. So moving on, process operations. Operation with typical numbers are as follows. So if I give 30-minute residence time, I start with 1 kiloliter of water. At the end of 28 hours, or we were targeting a day, we would have about 950. So the water recovery is almost 95%. And what has happened is that this is the volume of concentrate collected, which grows over time. The mass of surfactant removed is is this much total milligram in grams. And so that's almost 5 kgs there. And the concentrate volume, or sorry, the concentrate concentration is high enough to find some value in a lesser application. Okay, so these can be used for industrial cleaning, car, automotive cleaning, etc., etc. So the surfactant concentration in the treated water will decline over this time, and all the way from 5000 to below foaming. This is typically below 50. This minus values because I've used some equations rather than actual data to show you what would happen and what has been observed to happen. So here, if you did the same operation with a 20-minute residence time for the foam, what you would observe is that the volume of water in the tank, almost 50% has been taken out as foam, and therefore the concentrate collected has a much higher volume and its concentration is much lower. It's an order of magnitude lower. So while this might initially seem that, oh, we can do it very rapidly, you will not end up gaining much value, because a twofold increase in concentration, even a membrane separation can be tried. And these days, RO membranes are being used. You can concentrate. Of course, the fouling will be maybe significant and may need to be addressed before you can scale this up. But this is the advantage, and this is how the process can be operated to get the desired results. Next, I'll briefly mention the critical enabling technology for the system to work is a mechanical contraption we call the foam breaker. So that's electrically powered. It's an electrically powered device which we made locally, capable of collapsing foam based on our own designs, collapsing foam at a very high volumetric flow rate. And the foam breaker works on the principle of subjecting to the foam to a very high shear or a very high strain rates, which can vary from 5 to 50 kilohertz. Then a prototype device capable of collapse. So we had made actually the prototype devices right from a miniature scale, lab scale, to fairly large scale. So the power consumption would have gone up from 10 watts to more than 100 watts. Yeah. Because of the larger motor required to operate it. So we eventually, the last one, the one which we took the trial with in the factory would have the capability to collapse 300 liters per minute of aqueous foam generated. Yeah. So it was collapsing foam coming into the system was total 300 liters per minute, and it would be instantaneously breaking it into an air phase and a concentrate liquid. Now, this device can also be used to prevent the use of anti-foam chemicals. Eventually, I believe whatever we are adding to the water is a pollutant. We are adding. That's one of the I think big sort of advantages of the reverse osmosis technology. It purifies water, without adding anything to it. Because moment you add something, there is a consequence. It might kill the germs, but it will have some other consequences as well. So this doesn't, this mechanical system consuming electrical power, small amount, can be used to as a substitute for foaming waters. It can also probably be used, and I will present briefly a schematic, an idea. It can be used to address foaming in natural water bodies also, and other systems where undesirable foaming is taking place. Now, one of the things, other potential application is that you have uh, in washing machines, you may be knowing the main wash will take about say 15 liters. It varies with the size rating of the washing machine and also from top loading and front loading washing machines. But 75% of the water is the water used for rinsing. So you take in 15 liters for the main wash, throw it out, and then you take in another 15 liters, say, and use it for rinsing. But the rinsing is done thrice. The reason behind this is, and this is true for hand washing of fabrics as well, very low concentrations of surfactant in water produce visible foam. And for the consumer or the user of the washing machine, the absence of visible foam tells them that all the surfactant stuff is gone from the system. Now your clothes can be dried and you can. It can be used to recycle water within a washing machine, because the rinse water is a big water consumer in the washing machine scheme. Yeah, so one of the potential applications which was tried out also is its application within the potential of using such a system to recycle the rinse water within a washing machine. There were several granted patents around it. I've just briefly mentioned it. One of the reasons so this is in the public domain. And okay, now further, if you go a little further logically based on what I've just been saying, that if you let the foam stand, the water drains out and the surfactant molecules form like a dry structure, eventually collapsing. If that is true, if I age it even more beyond 30 minutes, I take it into hours, I should be able to get a neat surfactant out of it. Yeah, that's partly true. When residence time is more than greater than an hour, the foam films will thin down to critical dimensions at which the foam collapses. Now, typically, if I make foam and leave it in the bucket, over time, this will collapse back in the solution. But here, remember, I keep on bubbling air over hours. So new bubbles are generated, pushing and holding up the dry foam at the top. If you could arrange, set up a system such as that, the surfactant residue from the collapsing foam should be observable on the top of the foam. And that's what we observed. These are pictures taken in a lab in the collaboration. We can see the little patches of surfactant. In fact, when we first did this in a lab, we saw little globs of surfactant patches all around the tower. Yeah, so basically as the foam had collapsed, the surfactant separated out from this wastewater was, yeah. Of course, surfactant is not a huge high value chemical, but it still remains one of the more expensive ingredients in the mix of cleaning products. So it is possible to separate surfactants out of an aqueous solution without the use of membranes or heat. Of course, membranes consume much less power, but the life of the membrane has to be the same. Heat, of course, has issues because it can denature the surfactant but heating has been involved in producing thermal means have been used. Yeah, so I need not go into further detail. So that's another potential application of this. The other applications I would just try to mention here. One is that it can be used for in situ lake remediation. Yeah, so imagine we have this surfactant rich water in a lake. We need not have a big system. We can set up a tower and an aeration system below it. The bubbles, because being lighter, would rise directly up and get collected in the tower. Of course, the aerator has to be well covered with this tower, and the bubbles would then rise up and they could be channeled into the foam breaker, which would release the air and concentrate not for any use, it's just that this organic waste can then be dealt with but the the lake or the natural water body could be largely free of the surfactant. So I've just basic schematic I've made. This is the aeration system, the collection system, and this is the tower whose height vis-a-vis the aeration rate really decides the age of the foam. Of course, not all foams, the amount you can recover varies with the surfactant type and the molecular structure. Most of the commercially used surfactants generally tend to be linear molecules to get a high molar packing density at the interface. And for those molecules, it is possible to concentrate in the using the orders, the numbers I just mentioned. For molecules which don't display such high molar packing densities, the concentration effect may not be that much, but at least you'll do away with the natural surfactant or whatever it is. So there has to, first one has to appreciate there has to be a surfactant active molecule for a stable foam to get produced. Yeah. Then, okay, this thing is maybe we can use the mechanical contraption of its or its variations to recapture. So froth flotation is a possible improvement in froth flotation device. So here, so I will not detail too much here, just that we can actually probably drive out the foam-based separation that is carried out here at a higher rate or with higher efficiencies. There are these days also these I don't know to what extent they use in labs working on protein chemistry. The proteins also sometimes tend to come out in foam. And if you do it, so you have these devices which are called protein skimmers, which remove the proteins in the aqueous broth. And these also can, a similar technology can be used to maybe separate proteins from aqueous solutions. Yeah. So that's pretty much it. That's all I have got. So I'll be happy to take any questions, comments, or so I'll stop sharing my screen.
Thank you, Professor Jaydeep, for a very enlightening talk on separation of dissolved surfactants from aqueous solutions. The session is open for discussions or questions. Can opt to ask questions. This was a very practical topic. So one question we received is mechanical foam breaker a sonicator?
No, it's not a sonicator.
Okay.
It's not it's not a sonicator. It's a device for shearing the foam at a high volumetric flow.
Okay. Okay, one question I myself will ask. Till other people have some questions. You had shown this combination of mechanical system and others. Suppose this in a typical washing machine where fabrics are being washed, how costly or speed up we can achieve in removing the surfactants from water and recycle there and then?
Yeah, that's the critical step. Actually, the time it takes to carry out all the surfactant with the foam, even with the dry foam. So one of the limitations is the speed. As I just mentioned, when people see a demonstration of this technology, the first thing that strikes them is that to speed up the process, can we pass air at a higher flow rate? And I explained very well that's the limitation. Because if you take a very high flow rate air, which means you are pushing out, so the speed would, the duration of the washing cycle would distinctly increase if you wanted to recycle the water using this technology. So that's for sure. Yeah. So water, the time for the duration of the washing cycle would go up more than double.
More than double. Okay, fine. I mean, in near future, you expect this where like continuous process has been feeding water and clean it out as a process.
Sorry, I couldn't get the question.
Is the process which you have dotted, is this a natural limitation or is it technological, some advancement in technology can make it happen? That online we can remove the surfactant and keep on reusing it.
See, currently technologies, in my opinion, are available. We can remove surfactant with activated carbon also, but it would be very costly because you'd have to replace the activated carbon quite often. So there may be other technologies also, but the main advantage is when you have water like which is 1%, that's not typically the washing machine rinse water. But if it is 1% surfactant, this happens occasionally in factories, then you really have two issues. One is you're wasting away a lot of a valuable material. Second is it can actually cause damage to the existing treatment facility. So if you can pre-treat this high surfactant wastewater, then probably a situation where you can, which doesn't occur all the time, but when it does occur, it will save you a lot of problems downstream.
So one among the audience has asked the question. What about other emulsifiers like cosmetic going in water bodies, etc.? Does this system involve there also? I mean, cosmetic going in water.
I didn't. So you're saying oils?
So, yeah, probably emulsifiers like cosmetics. Okay, you can say first think about this cosmetics in water.
No, see, ultimately it only boils down to whether you have a molecule in the waste which is capable of supporting a stable foam. And that would happen only with the surface, what we call surfactants commercially. And those surfactant molecules generally tend to be linear molecules with a hydrophobic tail and a hydrophilic head group. The reason being is they give you large packing densities. Yeah. Unlike more bulky molecules which may have a hydrophobic moiety and a hydrophilic section, and also show some ability to get stuck at interfaces.
Okay.
So, yeah.
Fine. Another among the audience has asked clarification on this function of mechanical foam breaker between 5 to 50 kilohertz.
No, that's the sheer rate. I've just mentioned there is no. I mean, maybe that's.
Okay, there is a strain rate you will reduce in this.
Yes, it's per unit time. So it's like, if you calculate the distance gap between the shearings in the shearing system between the foam and the plate, which is causing it to collapse, that distance divided by the rate at which the angular velocity. Yeah. So it is nothing to do with sound.
Fine,
It's a
fine.
physical, mechanical system.
It's basically strain rate induced to break the foam.
Yeah, so it is actually a rotating disc. So the foam is impinging on a disc. It's disclosed in the patent. It's disclosed in the patent.
Any more questions? So we'll thank Professor Jaydeep for enlightening talk on this separation of dissolved surfactants from aqueous solutions. Thanks, Professor Jaydeep. And with this, we close this session number 4. We also thanks organizer for organizing it well. Thank you.
Yeah, thanks a lot.
Over to organizers.
Thank you,
Thank you.
sir. Thank you, sir, for chairing the session. Now we'll have a short e-break and we'll resume the session at 16:10 hours IST. Thank you.
All the participants are requested to rejoin the link due to a small WebEx glitch. I think none of the participants are able to share their video. I just request them to exit from the meeting and rejoin it to enable their video. I apologize for this small glitch. Kindly exit from the meeting and rejoin again. We'll meet exactly at 22 minutes at 16:10 hour IST. Good afternoon, Professor Jalian. Would you like to test your presentation?
Yes, yes, that would be perfect. Thank you. I'm going to share if you allow me.
I'm just in second.
Sure.
Yeah, your share button will be eligible, I think.
Yes, it is. So I'm going to see if I can share. I have many screens open as always, but trying to find out which one is that. So share that one with you. Yes, I think that's. Can you see that from your side?
Yeah, I can see that. Yes. You need to, I think, go to slideshow and yeah.
How does it look?
It's not the actual displaying board, I think. It is
I
the
know,
other
I know. What should I do? Let me close these ones. Maybe that would be helpful to close extra ones, but I noticed this yesterday in another talk also. I didn't have a full screen thing. I don't know why.
So there is this display setting. The second option, duplicate slideshow, you have to click that.
Thank you. So
Yeah.
always show yes.
Yes, it is perfect. Now you can change one slide. You can to see that.
So let me page it down and see if I go correct.
Yeah, it's going
Good.
down.
Okay,
Yes.
thank you.
Sir, I'll temporarily remove you from presentation. I'll
Yes,
show you
please.
your biodata and then I'll again make you presenter.
Thank you. Okay.
Sir, give us only 10 minutes. We'll just come.
Sure. I go around and come back in 5 minutes. Okay.
Sure. Thank you.
Thank you.